Okay, so the methods for this, there's lots, and within the physical sciences and engineering, the mechanistic and physical methods that they have available, we'll leave those to them. And they're out there. You may use them at some point, but really where we're going to focus on is agent-based and cellular automatons. So these are two different approaches. Agent-based is the most popular currently, and the basic idea is that you are creating computer agents. So in this case, I've got people in this picture, but you might have elk or fish or bees or flowers or trees. Anything that we relate to or that we're interested in studying could be your agent. And then we give these agents properties, and then these agents have a life cycle that they go through. So typically an agent is a point, just a point for, say, each salmon going up a stream. And then they could have attributes, their health, which often when it reaches a certain minimum, they then transition to death, size, age, sex, whatever it is that's important to your model. And then agents tend to behave independently. In other words, they move, they feed, they breathe, they die. Over the course of running the model, they go through these cycles. And then they can interact with other agents typically. That could be eating them, that could be breeding with them. They can also interact with the environment, so they can eat grass from the environment, or maybe they're going to prefer to move towards water instead of towards a drier area because they're thirsty. And then as their attributes change, they may no longer be thirsty and they move back to somewhere where they could forage. Within environmental science, there's two that are heavily used, and you may see these terms pop up: spatially explicit, individually based model. That means each model, each object in the model represents one individual. So the object would be a tree or an elk. Then there's spatially explicit population-based models. Each object represents some number of individuals. So this occurs when you have lots of individuals. So if you wanted to model all the herds of elk in California, you probably couldn't do it by modeling every single elk. It'd be too computationally intensive. So instead you model each herd. If you're going to model the wolves in California, you could definitely do them individually. There aren't that many. So it depends on the number of individuals as to which one you pick typically. Okay, and these terms you'll hear once in a while, not as much as we used to, but you will hear them. So simple model. Simple model might be that we have a predator, like our wolf, and then we have some caribou, and the caribou interact with each other, and then the wolf interacts with the caribou. So in other words, all of these would have an X and a Y coordinate, some location. The predator would have some internal variables like hunger, and the prey might have their health. And so then there's this interaction that happens, and typically we go through a cycle, a loop each time, updating time. And so as the predator moves towards one of the prey, it may start moving faster in that direction. If the predator's hungry, that would change how it interacts with the prey. When it's hungry, it would move towards them. When it's not hungry, it might just sit. The prey, similarly, when they're healthy, they would move away from prey very quickly. If they're not healthy, they might move slower. And these models can become as complex as the computation deals with. And of course, if the predator catches the prey and eats them, then the prey's health goes to zero and you can remove them from the model. Internally, there's typically a big loop, and this is an update loop where you would move the agents, then the agents interact with each other, like prey-predator interactions, and then you update the attributes. They become hungrier over time unless they fed. At some point, they might give birth, either because of age or because of being eaten. They would then die. And this tends to go for a long time. We tend to run models for quite a while. Movement is a key element to this, and there's different types of movement. Again, typically each agent has an X and a Y coordinate, and then you move it. The simplest way to move is simply random movement. Simply move them some random direction, which for a lot of models works really well. Then we have directed movement, where again, say an animal starts to become hungry, it would start moving towards its prey, or becomes thirsty, start moving towards water. If it became nervous, it might move into terrain to hide from something. And then there's potentially other forces that would influence its movement: wind, water, slope, other ones. One of the models that one of my advisors worked on at Colorado State showed that elk stayed away from big rocks and other things that wolves could hide behind. So that was them interacting with the topography. Animals, like humans, also tend to avoid steep slopes unless they're like Rocky Mountain sheep. Just to mention this, we don't use this too often, but every once in a while you might need it. The random walk is called Brownian motion, directed walk, moving towards a resource. And then the flight foraging hypothesis was important because there are some species, like there are species of seeds that will ride the currents on top of trees, and they will travel extremely long distances. So most of the seeds won't travel very far. They'll drop close to home, but a few might travel quite a distance, and then that could establish a new colony. We saw this with one of our students modeling Spartina seeds. This was Kelsey McDonald, and she showed that just a few Spartina seeds could actually make it all the way to Alaska. Obviously, most of them would stay in the bay, but a few could get out in the bay and follow the currents all the way up there and start a new infestation of Spartina. So sometimes those few seeds getting somewhere could have a huge impact on the environment. Okay, different types of interactions. Species interact with each other to breed, feed. Sometimes that's over a distance. In other words, at a certain distance, prey is not worried about a predator, and then as the predator gets closer, the prey starts to react and maybe move away. The predator might chase the prey, and until it gets within a certain distance, it can't feed. Once it gets to a certain distance, suddenly it can feed, and the prey dies. They also, again, interact with their environment in different ways. Now, when we really get into this, real interactions are complicated. These are some examples of what animals do. Up in the right is a lion that befriended I believe it's a baby deer, picture of a wolf eating a watermelon. And this is actually a movie of a gray whale who feed by going down on the bottom and scouring the bottom, basically sticking their head in the mud and then sieving out all the good stuff in the mud. These are very difficult to model, and fortunately we don't really have to model them because they're rare. With agent-based models, we tend to go after the simple interactions to model the basic behavior of a system. And then, of course, since we're looking at natural resource management primarily, that's where our funding comes from to do this. We're then modifying the system to look at different simulations over time, often doing it over and over again to see what the general trend is, to then see, well, what might happen with this migration pattern, or what might happen if we remove the invasive here versus over here, or plant an endangered species here versus here. What then could happen over time with the system? Okay, so a little bit more on how these work. Usually, again, you have this loop, and a key piece of it is how the agents update attributes. So hunger or health tend to go down when you have food. Hunger goes up without food, health goes down. Birth tends to happen at some cycle. One of the interesting things is if you're doing a life cycle model, often they just do the females because they tend to drive the success of the system, and you can pretty much ignore the males. They die if hunger is too high, or health is too low, or age reaches a certain maximum, or the conditions are too harsh. You can also have animals grow, learn. Plants can bloom and senesce, so they can go through these life cycles. If you're doing life cycles, like some colleagues of mine have done with ungulates, they are born, and then they go through some type of immature phase, and then adulthood, where they start to breed and produce new babies of some kind, and then eventually die. And so this life cycle can be built into your agents, and so you can watch populations grow over time. As an example, here's a riverine model of fish. And so the idea being that you've got upstream and downstream, and the adults come up, are non-producing until they start spawning. Then they spawn, they go upstream, and then you have the eggs, larvae, juveniles moving back downstream with different effects. So this is similar to what we might do for modeling salmon within a stream. There's a number of cool examples of agent-based models, and I think I'm going to stop again here.